In this lecture, we will learn how to analyze a continuous beam using moment distribution method. So this is the problem statement, that is, a continuous beam ABC is supported on an elastic column BD and is loaded as shown in figure. Treating joint B as rigid, analyze the frame and plot the BMD. So here we have 10 kilonewton point load on span AB and UDL of 2 kilonewton per meter throughout the span of BC, and there is no load on BD, and AB of 2I cross section, and BC and BD are of I, single line. First we will find out fixed end moments by considering each span separately. Span AB. So this is the span AB condition. Here we assume both ends are fixed. AB, therefore we will have fixed end moment due to this 10 kilonewton load. This is eccentric load, therefore here W AB squared by L squared is the formula, and here also W A squared B by L squared. Here A is nothing but 2 meter, B is equal to 3 meter. Therefore, fixed end moment MFAB is equal to, because this is anti-clockwise moment, therefore minus WAB squared by L squared, which is equal to minus 7.2 kilonewton meter. Similarly, MFBA is equal to plus, because this is clockwise direction, plus WA squared B by L squared, which is equal to plus 4.8 kilonewton meter. Next, consider span BC. In BC we have UDL of 2 kilonewton per meter. Therefore, both sides the same moment but with opposite sense of moment. That is, in B support we have WL squared by 12 anti-clockwise moment. In C support we have WL squared by 12 clockwise moment. Therefore, MFBC is equal to minus WL squared by 12 which is equal to minus 1.5 kilonewton meter. MFCB is equal to plus WL squared by 12 is equal to plus 1.5 kilonewton meter. So next step is to find out distribution factors. So for each joint we have to calculate the distribution factors. That is only internal or interior joints. So here we have only one interior joint, which is B. Therefore, at joint B we have 3 members meeting at B: BA, BC and PD. Therefore, first we have to find out stiffness factor for each member. So KBA is equal to 4EI by L, because the A support is fixed, therefore 4EI by L. And here I is nothing but 2 times I. Therefore, 4e into 2i by 5 is equal to 8 over 5 ei. Similarly, KBC is equal to 3 ei by L, because support C is simply supported or hinged, and I is equal to I itself. Therefore, 3i by 3, which is equal to ei. Similarly, for KBD is equal to 4 ei by L, because support D is fixed. Therefore, 4, which is equal to 4 ei by 3. Then we can calculate the summation, that is sigma k, which is equal to 59 over 15 ei. Now the formula for distribution factor DFI is equal to Ki over sigma k. Therefore, this distribution factor for BA is equal to KBA divided by sigma k, which is equal to 24 by 59. For BC, that is DFBC is equal to KBC divided by sigma k, which is equal to 15 over 59. Similarly, for BD, DFBD is equal to KBD divided by sigma k, which is equal to 20 by 59. So next step is to draw the table, the distribution table. So here we have joint A joint, B joint, C joint and D joint. And at joint A we have only one member originating from A joint, that is AB, and at joint B we have 3 members originating or meeting at that point, that is BA, BC and BD. Similarly, at joint C we have only CB, at joint D we have only DB. Okay, and here this for BA member, the further end is AB. Okay, this one. For BC, the opposite end is CB. Okay, member CB here. BD for DB. Okay, that we have to keep in mind, because while carry over, we have to put in appropriate end. So now we have to fill up the distribution factors already found for joint B and FEM, fixed end moment. So the distribution factor for simply support or hinged or roller is 1, because whatever the moment we have to balance it. Okay, therefore here 1. So the next step is to balance. First we have to focus on end supports, which is simply supported. In our problem, support A is fixed, support B is fixed, this B is interior joint, but C is the exterior joint which is simply supported. Therefore, we have to balance the stumpy support at first. So, here the moment should be equal to 0 at C, but we have right now plus 1.5. So, to nullify it, to make it 0, we have to apply opposite but equal. So, minus 1.5. This step is called balance. Okay. So, due to the application of moment at C, the far end, which is fixed or interior support, will get the moment of the moment as carryover member. So, the far end of CB member is BC here. So, under BC, we have to put half of this moment, okay, in the same sense. Therefore, minus 0.75 here. So, in this step, point that is joined C is now balanced. So, if you add up these two, we will get 0 moment. It should be, because the support C is simply support. Therefore, there cannot be any moment. So, now this C support is okay, perfectly correct. Now, we have to focus on other joint, interior joint B. So, at this moment, the joint B is not in equilibrium. That is not satisfying sigma m is equal to 0. Therefore, we have to make it sigma m is equal to 0 by applying some moments, extra moments, but in opposite sense. Therefore, here the net moment is plus 4.8 minus 1.5 minus 0.75. So, add these three. So, the net balance or net moment is equal to plus 2.55. So, in order to make it 0, that is sigma, satisfy sigma m is mb is equal to 0, we have to apply minus 2.5, so that the moment at joint B is 0. Algebraic sum of moments will be 0. But that minus 2.55 moment will be distributed because this joint has 3 members. So, the extra 2.55 kilonewton meter moment should be distributed according to the distribution factors. Okay, that means 24 over 59 parts of 2.55 should be applied to BA. Then 15 over 59 of 2.55 should be applied to BC member, and 20 by 59 of 2.55 should be applied to BD member. So, that step is called as balance. Therefore, here we have minus 1.04, here minus 0.65, here minus 0.86. Sorry, totally of 2.55. Okay. So, because of this balance, the far end, which is either fixed support or interior support, will get carryover moments. That will be the next step. So, we apply minus 1.04 in BA. Therefore, half of this moment will be transferred to AB. Okay, AB. So, here minus 0.52. Similarly, for BD member, BD to DB. So here half of this 0.86 minus 0.43. Okay. But there is no carryover from BC to CB because CB is assembly supported. So it cannot take any carryover moment. Clear? Okay. Now, in the balance step, joint B is balanced. There is no extra moment. And joint C also no extra moment added. So it is already in equilibrium. And joint A and joint B are fixed supports. Therefore, it can carry any moment. There is no problem at all. No need to balance anything here. Therefore, by this step carryover, then the distribution factor process is over. Now we have to calculate the final moments by summing up all the moments in the vertical column under each member. Therefore, moment in AB or MAB is equal to minus 7.2 plus minus 0.52. That will be the final moment here. Similarly for BA, for BC, for BD. Okay. So here only minus 0.86, here plus 1.5 minus 1.80, this is 0.4 here. Okay. And remember here, at joint B we have three members meeting. Therefore, the net moment should be equal to 0. Here plus 3.76, here minus 2.90, here minus 0.86. So it is equal to 0. This is a fixed support. Okay. This is the hinged support, therefore 0 moment. Final moment is 0. So the next step is to do the force calculation. Okay, in order to draw the shear force diagram. So for force calculation step, we have to consider each span separately and drawing the free body diagram of span AB. So this is the free body diagram of span AB. So here we have 10 kilonewton meter, and here moment MAB moment minus MAB, therefore anti-clockwise direction. Here BA plus 3.76, therefore this is a clockwise moment. Okay, this is the reaction at A, this is the reaction at B. Okay, RA or BA. We have to find out the values of RA and RBA. Since this is a determinate structure, we can apply equilibrium equations directly, that is sigma m is equal to 0 and sigma v is equal to 0 to find out these two values. So applying sigma m is equal to 0, RA into 5 minus 7.72 anti-clockwise direction minus 10 into 3 plus 3.76 clockwise, which is equal to 0. Therefore, RA is equal to 6.79 kilonewton. Now applying sigma v is equal to 0, upward loads is equal to downward loads. Therefore, RA plus RBA is equal to 10 kilonewton. Already we know RA, therefore RBA is equal to 10 minus RA, which is equal to 3.21 kilonewton. Next, consider span BC and drawing the free body diagram. So here we have BC, and at B we have MBC moment minus 2.90, that is anti-clockwise direction. At C we have 0 moment because this is simply support or roller support, therefore 0 moment, and UDL we have. So this is again determinant structure, so which can be analyzed only by equilibrium equations, that is sigma m is equal to 0 and sigma v is equal to 0 to find out the values of RBC and RC. So apply sigma m is equal to 0. Okay, so at joint C we have RBC into 3 minus 2.90 minus 2 into 3 into half of 3 meter, that is 1.5 is equal to 0. Therefore RBC is equal to 3.97 kilonewton. Now applying sigma v is equal to 0, that is downward loads is equal to upward loads, or upward loads is equal to downward loads. RBC plus RC is equal to 2 into 3. Therefore RC is equal to 2.03 kilonewton. Next, consider span BD. Drawing the free body diagram. Here there is no external load, but we have moments, end moments. So at B we have minus 0.86, that is anti-clockwise, and at D we have minus 0.43 anti-clockwise, and of course we have some reaction at D, RD, and at reaction at B, RBD. And we assume this HD direction, horizontal force at D, here positive sense, here also HB. We don't know the values, therefore initially assume the direction, this direction. Again this is a determinant structure. Okay. Therefore we can apply the sigma m is equal to 0, not exactly determinate, but we can use still the equilibrium equations to find out the values. Okay, by considering the whole structure also we can easily calculate the reaction values. No need to apply any compatibility equations. So sigma m is equal to MP is equal to 0 gives the horizontal reaction at D is equal to minus 0.43 kilonewton. That means the minus indicates that our assumed direction is not correct. That means HD is acting towards left in this direction. Okay. Now apply sigma H is equal to 0. Therefore HD plus HB is equal to 0 based on the assumed direction. Okay. So here we have to substitute the values. HD is equal to minus 0.43 here. Therefore we will get HB value. Therefore HB is equal to minus HB. HB is equal to minus HD. Therefore minus into minus 0.43, which is equal to plus plus 0.43 kilonewton. That means our assumed direction is correct. That is acting towards right. Okay. Now apply sigma V is equal to 0 for the entire frame. Okay. So here we have RA, already we found the value for RA, here RC, here RD. Clear? Because we are going to apply only sigma V is equal to 0, therefore we are not considering the horizontal reactions at supports D as well as A. Okay. Therefore only B. Moment also we are not considering here. Therefore not shown in this diagram. Only vertical reactions shown. Therefore, sigma V is equal to 0 gives RA plus RD plus RC is equal to 10 plus 2 into this 3 meter. So already we have calculated RA and RC. Therefore, RD is equal to 7.18 kilonewton. Now bending moment diagram. So this is the frame, and at first we have to note down the support moments. So at A we have 7.72 negative, and at B, that is BA plus 3.76, therefore up we have to note down and just join by a straight line. Again for BC, we have in BC we have minus 2.90, that's by convention we have to draw on the upper side, therefore 2.90 here, and this is 0, therefore join. Here also B, BD, and at B we have minus 0.86, therefore upside. Okay, we are standing here, therefore this is upside, and here minus, therefore down 0.43. So join by a straight line. So this is the support moments. Now we have to overlap the simply supported moment. Here we have point load, eccentric point load, therefore WAB by L formula, which gives 12 kilonewton meter under the load. So 12 kilonewton meter. So triangular distribution. Similarly, for UDL, the maximum load at center is WL squared by 8, which is equal to 2.25. So the remaining portion is our net bending moment diagram. Okay, this portion minus, this is positive, this is minus, this is positive, this is negative. So this is our BMT. Next, shear force diagram. So draw the beam APC, and just in support A we have upward force, therefore 6.79, and there is no load at all here between A and the load under the load, therefore now drops to 10 kilonewton. Again there is no load straight, then up RBA. Now RBC, okay, this is UDL, therefore gradually decreasing to this point, 2.03. Again up, RC is up. For BD member, okay, at B horizontal force is there, so 0.43. At D also we have horizontal force Okay, therefore point. And remember here, this reaction at RD gives the axial compression in BD member. That won't make any shear force. So for BD member, only horizontal force will make the shearing. That's why we consider for BD member horizontal force. Okay, that is the force which is perpendicular to the member. That we have to consider for shear force diagram. For AB and BC, we consider the reaction, vertical reaction. Okay, only vertical force to the member will create the shear force. So this is the shear force diagram. Okay. So in the next slide, next lecture, we will see other wattle frame